Let me introduce Eugene Burmako, who is the author of scala.meta and who is working at EPFL in Martin Soderski Group. So please welcome Eugene, and Eugene, you can start.
All right, thanks guys. Courtesy of Adobe Acrobat Reader, we can finally begin. It's great. I'm really thrilled to be presenting here today. It's a very unusual event for the Scala community, and I'm so hyped that it got organized so that we can sit together, all tool authors here in one place, and discuss the future steps. Quite awesome. So today will not be a typical presentation of mine. I'm not going to be, promoting scala.meta or something. Today I would like to discuss the problems that we solved and the issues that we faced, so that together we can come up with solutions. So 2 years ago in Berlin, during our presentation, Dennis Shabalin and myself, we presented a vision of a better metaprogramming API, something that would fix problems that plague Scala Reflect. Some of them were brought up during the previous presentation, thanks to Matthias. And it was quite fun. We got a very positive feedback, and we got to working. And a year later, at the San Francisco Scala Days in spring 2015, we presented some working results. Though today, and there we had some demos, there we had some working stuff, but today, as I promised, would be a bit different. So please put your hard hats on, because we're really gonna dive into the details. And just to sum it up, what's coming right now, it's all gonna be about ASTs. So the problems that scala.meta promised to address, the problems that it addressed, it's about abstract syntax trees. So it's the only thing that we need to get handled, in my opinion, and let's see what aspects it touches. So first of all, syntax. Well, there's this common problem with Scala Reflect, that it does not precisely represent all the syntax that Scala has. As Matthias brought up in the previous presentation, for instance, we have for loops. And if you just create a quasi-code that represents a for loop that you can see on the slide, then in the printout you will see that there's no for loop at all. It disappeared. So you have some maps, you have a lambda that you never wrote. So that's quite a weird thing. Of course, once you get the hang of it, once you develop the compiler for a few months, maybe years, it's totally natural, but I understand how off-putting this can be to the newcomers. And really, it's not the bug in the tree printer that the Scala compiler uses. If we take a closer look, if you use this show raw functionality, then we see that there really is a call to a method called map, as signified by the highlighted part of the printout, and there indeed is a lambda expression. So it's not a joke. The Scala compiler just takes these for loops and throws them away, replaces them with whatever it sees fit. So that's one aspect of the representation that Scala Reflect uses for Scala syntax. Another aspect is that it's really weakly typed. So even though Scala is a typed language, we have types. We're not Python, we're not JavaScript, but our trees, they don't think so. So if you take a look at this printout, let's just see what's going on there. So there we create a list, a reference to the list, like Scala list, and on the second line we splice it to create a constructor that will bring up the list of 1, 2, 3. But if we try to type check this code, if we try to evaluate using the toolbox functionality, then we will get a type error, which is kind of amazing. It says like the Scala list is not a value, type is not a value. What's going on here? Even though you can see that the printout there on the second line of the REPL says list of 1, 2, 3. Somehow the compiler does not think that it works. So actually, what happens under the covers is that the Q quasi-code, it creates terms, that is expressions, whereas the TQ quasi-code, it creates types. So what happens on the first line is that we mistakenly created a reference to list the type, not list the term. And therefore, now we can understand the confusion of the compiler. So somehow with the ASTs that Scala Reflect provides, it's possible to create trees that no one can write in the source code. And therefore, you can get very funny problems. And the final aspect of the representation that Scala Reflect uses is that it's, just funny, plain weird. For instance, if you try to take a look how classes are represented in the compiler, so that's probably the first question that every student asks me who works on a project with me. What's this def init? What's the param accessor and stuff? So this very, very simple Scala code, it gets desugared by the compiler in a pretty weird way. So that's the problem that we have, and this is something that all of the tool authors definitely recognize. So what do we do about it in scala.meta? Well, in scala.meta, we just bite the bullet and represent the entire syntax. So it turns out that Scala is a huge language, and it has a lot of funny corner cases, and you have to handle all that. But you just do. Otherwise you end up with this, which is not good. Anyway, so let's see what scala.meta thinks about the for loop that we saw earlier. So if we write it as a quasi-code, as a scala.meta quasi-code, so here I don't provide all the imports, they would take some place. If you're interested in details how to use scala.meta, you could go to GitHub. We have a tutorial there. The repo is called just like that, scala.meta/tutorial. So anyway, let's get back to the example at hand. So if we see the printout, then we get an impression that everything is all right, and that scala.meta has captured the for loop. And indeed, that's what's going on. So let's follow the highlighted parts of the printout. We see that the for yield construct, because actually there's no for loop, there's the usual for loop and for yield loop. So it's captured in the for yield AST node. Then we see that the x arrow list 1 to 3, which is actually called a generator in the language specification. It's got its own AST node, so we don't model it with a lambda expression, nothing like this. And finally, the x multiplied by x is just what the user has written. It's an infix application. And by the way, this showcases another aspect of scala.meta. So there's a difference between an application and an infix application. That is an application without a dot. Well, this is some of our more intricate detail, but this shows the level of attention that we pay to syntactic differences. And so another thing that I would like to mention here about this printout before we move on is that scala.meta trees are safe by construction. So unlike Scala Reflect trees, in which you can stuff like anything you like. So I don't know, you can take a class and then apply it to a type, and the compiler will just accept that. Well, until you type check stuff. In scala.meta, everything is strongly typed. So as you can see, the reference to a list, it's represented with a term name, which means that the compiler really expects a term there. So if you try to stuff a type, inspired by our previous mistake with Scala Reflect, it will be a static compilation error. So that you won't even be able to write this meta program that does this error stuff. Okay, so this I guess sounds pretty exciting, especially to those of you who've invested in tooling. So what does it take to how did you arrive at that? What did it take us to do this? Well, as Matthias prompted, we just wrote everything from scratch. We wrote the parser from scratch, and we designed our own ASTs. And scala.meta does not depend on anything, so it's self-contained. And the effort is actually pretty acceptable. So first of all, in order to get all the ASTs handled, in order to analyze and model the Scala syntax, so we just went through the entire Scala specification, which is a bit imprecise, by the way, but finally we figured it out, and several months later, Dennis and I, we arrived at something that we could use. Afterwards, we just took the standard Scala parser that's provided in the Scala compiler, in the Scala repository, and modified it to emit our trees. It wasn't trivial, it wasn't weekend, but it's not that much of an effort. And finally, this is something that I didn't cover today. These very precise abstract syntax trees, they make it very easy to implement quasi-codes. So quasi-codes, they were implemented by a GSOC student who did a project with me last summer. And it's quite amazing because the guy, he did not have experience with Scala before, and we've been able to do this cool stuff. in comparison, in order to implement quasi-quotes in Scala to 11, it was necessary for Dennis, my colleague who's currently a PhD student in Martin's lab, to spend 2 semesters on semester projects, plus later on an internship at TypeSafe. And Dennis is a pretty knowledgeable guy in the compiler, so what he produced is like several thousand lines of code that handle all the intricacies of Scala Reflect. So it's quite impressive that these new trees, they can speed things up that much. And finally, the great point about re-implementing things is that they end up being self-contained. So we do not need to track the changes in the Scala compiler to have our own integration builds that check that no one broke anything in the compiler, so that we need to fix it up, as Julian mentioned in his talk. So it's completely self-contained. Quite a nice aspect. So now let's take a look at some practical implementation of the theoretical concept that they've covered before. So it turns out that the scala.meta trees, they're so useful that there's some functionality that you cannot do otherwise with existing tools, and therefore Codacy.com, the startup that does static code analysis, they decided to work with us together and base some of their Scala patterns on our technology. So unfortunately, I won't be able to present today with my laptop, so I won't be able to show this stuff, and probably you cannot read this. This slide wasn't meant for that. But you know what? Let's just be, let's make an experiment. Maybe I can take the laptop that I didn't see before and try to make it work. Okay, so far so good. All right, we just need to go to the website. Oh, it'll probably need my password, which I guess is a game over, but Java update is available. Oh man, I need to log in. No, I guess this is a showstopper. Well, anyway. Maybe sign up for free. Okay, let's do this. We still have time, so. And after all, this talk is so theoretical. Oh, no credit card required. That's good. Yeah, I think they will still need my password, and it's like 30 characters long. Anyway, maybe next time. Maybe next time. And if you're especially interested, please find me later. Not this one. Okay. All right. I'll need some help here. Thank you. Okay. All right. That's good. So anyway, you will have to take my word for that scala.meta is amazing, and so amazing that people are actually using it. All right, let's move on. So it's all cool, but I do not want to make an impression that scala.meta is, a production-ready, flawless technology that just works and there are no issues. As I mentioned, one of the goals of my presentation is to bring up the problems so that we can solve them together. So one interesting challenge is something that I mentioned before a few minutes ago, is that Scala syntax is hard, and sometimes you have syntactic constructs, two syntactic constructs, for instance, that look the same, but in fact they do not behave the same, and you actually have to bite the bullet and do something with that. And so there's a constant tension between modeling everything in exactly precise fashion and just going crazy because there's too much stuff. And here's just some fun examples. For instance, you all know that you can use patterns when you're declaring vals and vars, and you can also declare vals and vars in the usual fashion. Just say val x equals 42. So there's a big temptation to unify them, to say, okay, so you say val and then you write a pattern and then you write the right-hand side. But unfortunately, it's not like that, because if you say val capital X equals 42. Then capital X is not a pattern, because it's not how pattern matching in Scala works. So this kind of funny things, some of them are listed here, and others you can find in the documentation to our project. It's something that makes our life harder. So I would be really interested in opinions of people who've designed their own ASTs for Scala, like we've seen in the Scala Reform project or in Scala Refactoring partially, to see how we can improve here. The second challenge is actually the consequence of something that I boasted about. So we have very precise trees, and they're all amazing. But now you have this thing that a lot of Scala constructs that you could handle uniformly, for instance, infix method calls and usual method calls, you cannot handle anymore. So here on the first line of the printout, you can see that we take an infix application and we try to match it with a quasi-code that says, well, usual application. You get a match error. And that's right, because these are two different ASTs. And well, that's the crux of the problem here. That we're moving from abstract syntax trees, the A thing in the AST, to concrete syntax trees. And it's not quite clear what are the best ways to deal with those concrete syntax trees. So maybe there's just no universal solution for that. Maybe we need multiple flavors or quasi-codes or something. And this is something that we can learn only in practice. So we definitely need your help with these guys. So if you use quasi-codes, if you use a syntactic API of scala.meta, and you have any ideas how to improve that'll be awesome. And finally, this is not a challenge, but well, it's a small one. But I had to include it so that I don't sound too depressive. So actually, Scala is a vibrant language, and it's evolving quite fast. So we have the 2.x family of languages, 2.11, 2.12. There are some planned deprecations of some features, syntactic features like procedure syntax. And on the other hand, we have DOTI, which is something completely new. So currently, it supports more or less the same Scala that we know and love, but later on it will have additional stuff. So how do we handle all this? Well, we need just right off the bat, we need to build this notion of dialect into a common library of ASTs, so that we can handle multiple versions of the language without rewriting the parser or something. Okay, so this is more or less it about the syntax part, and now let's move to something non-traditional, tokens. Well, one problem with Scala Reflect, and again, I'll refer you to the earlier presentation by Matthias, is that with Scala Reflect ASTs, they don't provide you ways to reflect on the underlying representation of code. So you cannot see white spaces, you cannot see comments, nothing like this. And we can just create a quick experiment. So if you write a comment in a quasi-quote, then it just disappears. It's not there. Well, that's because ASTs, they cannot represent this stuff, at least in Scala Reflect. And so this is something that I heard during Matthias's presentation. Okay, but we have positions, so everything's fine. Well, both yes and no. So let's make another experiment. So if you invoke Scala compiler with the xprint pause option, which is highlighted there up in the blue, then you get positions generated for all the ASTs. Again, they're in the blue. So next to all the ASTs, next to all the fragments, expressions, definitions, whatever, you get these numbers. And well, typically they're fairly accurate, so it's not like they're completely off. But there's one issue. So they still do not include comments. So if we take a look at the range for class C here, then it starts with offset 11, and the comment is at offset 0 or 1. Which is, well, definitely a problem, because imagine if you're writing a tool that wants to generate Scala docs from Scala code. So you start with the offset 11 and you think, oh, okay, just go back, and I arrive at the Scala doc. But what if you have a comment in between? What if you have line endings? What if you have white space? So you actually end up re-implementing a big chunk of Scala's lexer, which is not good. And another interesting thing about positions is that positions, they don't tell us everything. So if we focus our attention on the position for x, which is 19 to 25, then we will see that x here, that this position, it not only covers the name of the parameter, but it covers the whole section of the definition. So I think it goes for x:int. But what if we are inside an IDE, we put a caret on x, and we've hit rename? We just need to select the name itself, nothing more. So that's a problem. Again, we have to re-implement parts of the lexer. So just the bottom line, the fact that Scala Reflect does not include any support for tokens or something like this, it's a fundamental problem, and you cannot just fix it with positions. It's just not gonna work. All right. So as a result, if you want to do something that at least barely involves white spaces or comments, you have to write your own stuff. Either you have to base your work on Scala Reflect. This is how it's done in Scala Refactoring. Or you have to write the parser from scratch, like it's done in Scala Reform. The parser and the ASTs that track those tokens. So what scala.meta provides, it's fairly simple in hindsight. You actually get to access tokens. And well, as objects, as normal objects, not as some numbers that are emitted inside of the Scala parser, but actually as objects that have positions and stuff. Well, again, you don't have to take my word for it. Let's take a look how scala.meta works. So here we see that if we parse a chunk of code with the scala.meta API, which I would like to mention is quite easy to use. So you just say parse and say what result you want to have. So here stat means a statement. This is quite an improvement, to be honest, from the Scala Reflect API, where this kind of things, they take typically 5 or 10 lines, depending on how you approach that. So anyway, we see that after parsing, we get this comment in place. So how does it work? Well, indeed, we have tokens for all that stuff. And in particular, we have a token for a comment. So here you not only can see the string, but you also see the range. So it starts with 0, ends with 10. So as I predicted, 11 is the start of the class keyword. And if inside the ID you are standing on X, and you press rename, then you can immediately see what's the span of the name, because there's a dedicated token for that. And if you need to jump to the previous token or to the next one in order to do some refactorings, you can do all that. You just go back or back and forth in the token stream. So here you see that really every piece of Scala code, it ends up being a token or a part of a token. So that's quite interesting, and I guess you can already imagine what you can do with this stuff. So what did it take us to implement this? And as I mentioned, yes, please.
So is the token attached to the class def, or it's the same level, a sibling of class def?
Okay. So the question is, what happens to the, well, how do we get from a class def AST to the documentation comment? Well, for that, you have to drop down to the level of token streams. So you say, what's the first token of class def? It'll be, the class keyword or an annotation or whatever. And then you go back, you skip all the white spaces, and you arrive at the documentation comment. So the benefit here is not in the fact that we automatically somehow magically come up with an algorithm to attach documentation comments to ASTs. I will talk a bit later about that. But the trick here is that we provide a structured approach to traversing tokens in the file. So when you reify tokens as a collection of objects, then you can manage these collections as usual lists or anything you have with Scala tools.
But the tokens are attached to trees, so that means there's not a stream of tokens, there's a tree of tokens, right?
Okay, so another question is about the structure of tokens. So is there a stream of tokens, is there a tree, or how does it work? So the current implementation, it works as follows. You have a tokenizer, which emits a stream of tokens, and then you have a parser that reads the stream, and then builds up ASTs. And while the parser builds the ASTs, it remembers the indices of the first token and the last token of an AST. So ultimately, tokens, they do not belong to the tree structure, but you essentially get views into them. All right, so another question?
Okay, so
as this is the same area, I mean, if I have like two variables in the same line, for example, or two values in the pattern, anything, and the comment is in between them, and it is like the top level of my class. It's not like here in this quasi-code example, but I'm traversing the tree and I'm somewhere in the middle. So if I'm where the token will be, on the first value or on the second? I mean.
Okay, so that's a very good question. The the point of where to place tokens and how to associate them with ASTs is kind of an open problem now. So now it's very implementation dependent how the parser implements that. But it turns out that there's a great heuristics that covers this. So we'll get to that a bit later. All right. Okay, another question about tokens. Excellent. No, but it's amazing. Please ask questions. We can just cut the presentation short. It doesn't matter anyway.
I'm asking because of this refactoring library, if it uses meta, aren't we afraid that this representation is too detailed to be feasible for a PC to perform some, let's say we want to hack on Scala library itself? Yeah,
that's an amazing question. So what about efficiency? Yes, that's indeed a concern. If you ray-file the tokens, imagine you have a file, auto-generated file with like millions of characters. So what happens? Bad things happen, but we do know how to address that. So our current model, it was inspired by what guys at the Roslin team at Microsoft did, and they do pretty similar things, and they have acceptable performance. So currently we have a naive implementation. We just the tokenizer, it really emits a collection of tokens. So it creates objects for all of them and creates, Scala list, well, a vector to be precise, and that's that. But of course, you don't have to do this explicitly. You can ray-file tokens on demand. So if someone is interested in looking into the contents of the file, then sure, let them do that. But by default, we can skip this. I'm fairly sure this works. This just needs some time for implementation. So any other questions? Okay, so let's move on to implementation stuff. So how much time does it take to implement this from scratch? Well, unlike ASTs, tokens are fairly simple. So you have a well-defined Scala grammar. Even though the spec doesn't cover everything, it covers a lot. So just within a couple of days, it's possible to create all those case classes for tokens. But of course, in order to get acceptable performance, you need to work hard. And I think it'll take us several weeks or maybe more than a month to get this handled. And finally, as I mentioned previously, in order to support new ASTs, we just took the old parser from Scala Reflect and we modified it. We did the very same thing with the tokenizer. It took us a while because, man, that's probably the hairiest part of the compiler. But yeah, still the effort is acceptable. And again, I want to bring this up again and again, that this part is self-contained. You don't have to interface with any compilers. You can write everything on your own from scratch within several months, as we've seen, which is a pretty much okay solution. Now, demo time. So what kind of tools can you build on this? So I have a master's student this semester, Olaf Gerson. He's working on a Scala FMT tool, which is inspired by Dart FMT and Go FMT. The school opinionated programs, and in order to motivate the choice of the project somehow, you can take a look at this tweet by Victor, where he says that we should not actually argue about styles or something. We should apply them automatically, and that's quite an amazing strategy because I know firsthand how hard it is to consistently apply the same coding style across the project. And quite often it happens that someone submits a pull request and then someone says, okay, fix the formatting, the indentations, 2 spaces, something like this, which is pretty stupid if you think of it, because programs can handle that. And so Olaf went ahead and actually wrote a program whose interface looks roughly like this. So it takes Scala code, it takes some configuration, and then it formats the code according to the config. So unfortunately, without my laptop, I won't be able to demo the functionality. But I really urge you to just Google Scala FMT, and you'll get the GitHub website. It has a demo. It has a GIF which approximates the demo and outlines how this thing works. It's quite interesting because it ended up being a graph problem, which is not very obvious if you think of it. But anyway, tokens were really instrumental here. Because if we did not have representation for all tiniest details of Scala syntax, and if we could not map them to concrete syntax trees, it wouldn't be that easy. All right, so speaking of challenges, and this is something that's been brought up before. So There are these tokens which are called trivia. I'm using the terminology of the Roslin team. Well, trivia is something that does not affect semantics, like white spaces, except in the situations where new lines are semantically important, or comments. So what goes there? There they have a really amazing heuristic. So all the trivia, if I recall correctly, an AST node, it owns all the trivia, that is white spaces and comments, up until the end of the line. And when the new line starts, then all the trivia gets attached to the next node. So in our case, if we see this printout, def z equals 3, it will get the documentation comment, it will get its own indentation, and it will even get the empty new line before. This is quite handy because if you write a refactoring tool, and we definitely tried to do that, some of my students at EPFL did that, when you remove the def z node and move it elsewhere, then this heuristics, it allows us to remove all the unnecessary indentation as well, which is quite amazing. So at first, when I read the paper written by the Roslin team, I thought, oh my god, this is so arbitrary, probably we can just ignore this. But yeah, now I think completely differently. This is a very good idea. And another thing is, when do you want to work on the level of tokens? This is non-obvious, to be honest, because if we work with abstract syntax trees, we get the benefit of structured approach to code transformations. Because if you work with ASTs, you can never mess up the syntax, like you can, for instance, if you do C macros. But tokens, they don't provide the safety guarantees. On the other hand, industrial experience, for instance, the experience of Clang format guys, it says that sometimes you just drop down to the level of tokens, you do a few changes, and that's it. And otherwise, it would take a lot of AST manipulations to express that intent. That's interesting, and we definitely need more experience about this. So this is another place where your feedback would be very, very valuable. Okay, so I see that I have just 5 minutes left. So let's make this real fast. Let's see. I'll probably have to cut short, but well, I'll try to summarize. So anyway, semantics. What's the biggest problem with Scala Reflect? And again, as Matthias pointed out, some of the features like named arguments, hate them also, they get desugared by the compiler. And then you, as a tool writer, you need to figure out what this thing means. And so let's see how it works. I have another example with the for loops. So actually, when you type check the for loop, then you get even more stuff. So if you thought that the previous representation of a for loop was scary, then well, it's time to reconsider your position. So everything that's highlighted there in the blue, it's something that the compiler has invented, which is quite sad because as a tool author, this is something that you have to uninvent. Very, very hard. I mean, I don't know how to do this myself, so I tried. Well, later we will get to that. And the most amazing thing about these desugarings is that they vary between even minor versions of the compiler. But okay, so let's see what happens if we bump a major version of the compiler. What if we take a look at Dotty, which supposedly will become the future of Scala or not? Well, let's see how it goes. So in Dotty, it's even more stuff, which is quite interesting. And as you can see, the lambda is represented as some sort of anonymous function plus a closure. Well, this is some fun thing. So if you write macros, you probably will be excited about seeing that. Anyway, so definitely that's an issue. So what does scala.meta have to offer here? And that's probably the toughest part of the implementation, honestly. So we actually have to bite the bullet and provide the platform-independent model of Scala semantics. And just let's take an example and see what I mean by this. So if we take a look at the for loop example that we've seen before, and if we print its semantics, I probably won't get into the details how it's implemented exactly because we don't have that much time. Though we will see what the numbers next to ST nodes mean. As you can see, there's a bunch of numbers in different brackets. So they all make sense, and they're all part of this platform-independent representation of semantics. So first of all, we have brackets, and brackets represent denotations. That is essentially resolved names plus something that we call prefixes, something that goes before the double colons. I won't have time to address that. But anyway, if you take a look, then we see that all the occurrences of x, they're bound to the same, blue thing that says local variable blah 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 some unique ID. So that's scala.meta's way of saying that all the occurrences of x, they are bound to the definition of x that is captured by the clause of the for loop. And then we see that the list that we wrote there, just as an identifier, it means Scala collection immutable list. So actually the notations, they're just fully qualified names. Well, more or less. There are some intricacies. And finally, another example is the green text that stands for that signifies the multiplication operation. So there we can see that it's a method which is defined on an integer, and it takes another integer and produces an integer. So as we can see, the notations not only contain fully qualified names, but they also contain method signatures, which is very useful. Another aspect of this representation is this curly braces. And curly braces, they stand for types. Of course, there are a lot of types involved here. I'm not including all of them, but for some of the our old acquaintances, like this term name x, we can see how it goes. So we can see that the type of x, it's int. Well, fair enough. But an interesting thing about this type is that the type is also a scala.meta construct. So therefore, it has all the semantic information of scala.meta. In particular, we see the square brackets 4, which means that it's scala int, not some other int. This is something that we haven't seen in the printout here because I cut short, but trust me on this. And finally, speaking of the list, we can see that list is really a Scala object. It has a singleton type. And again, we get a bunch of these various braces which signify that a list is probably a Scala collection immutable list. It has a type of itself. So see, this list is typed as curly braces 2. So this is a recursive type. And finally, we get to the angle brackets, which represent the sugarings. So speaking of the sugarings, what I can say is that in scala.meta we do have the sugarings because they're useful. But on the other hand, we hide them by default so that they're like on demand. If you're interested in them, you can access them. And here you can see that the list thing is actually a desugaring of list of int because we infer a type parameter there when we create a list of 1 to 3. And that list of int is actually desugared, as you can see by the angle bracket 3, into list.apply. So all the intricacies of Scala semantics, they are taken care of, but they're neatly organized in a platform-independent way. So that they don't get in your way when you don't want that, but you can always access them. So that's the kind of representation that I had in mind for scala.meta. And I think that if we work on it together, then it has a chance to become like the lingua franca for tool authors, which is a very exciting prospect. Anyway, I'm going to skip everything and jump straight to the conclusion. So first of all, what did we learn from the scala.meta experiment? What's useful there? Well, we can solve almost all problems of Scala Reflect by just introducing better ASTs. And other problems, they are reduced to AST problems, and then we solve them. So I think that the future is pretty much bright because we got the idea how to handle the weirdness that everyone's has seen on their own. And there are two big avenues. The first one is the syntactic representation of Scala code. And we see it works fairly well in the sense that we can implement all this functionality, the parser and all the new ASTs and the tokenizer completely in a standalone way. So we don't have to interoperate with any compilers, any projects. We don't have to synchronize with the release cycles, nothing like that. This is great. But on the other hand, in order to produce this nice semantic model, we actually do have to interoperate with type checkers because even though Julian advocates writing a type checker from scratch, well, I would not undertake this task. Probably my life is too short for this. So anyway, we have this module that we call a converter, which takes Scala Reflect trees, for instance. It interoperates with all platforms, like IntelliJ would be another example. So it takes platform-dependent trees and it converts them into platform-independent representation that we've seen with all this, curly braces and stuff. So that's really hard. And this is something that I skipped, but I'll have to go back there because it's well, a very touching story. So at first, when the project just started, I thought, oh, it's gonna be super simple. I know Scala reflectories, well, quite well because I was working on macros and stuff, and then I'll just write the converter myself. It'll be fine. I spent several months with that thought, and the result I just had to throw away because, well, it had some problems. Then I started from scratch again, armed by the knowledge that it's not that simple, and I'm not still there. So it's like, you know, it took half a year, and there's still issues. So probably this thing, it needs a fresh look. So this is why I'm so excited about the chance to speak here and then discuss this later. All right, and finally, to conclude, I would very much like to thank all the guys who contributed to ScalaMeta, all the students from EPFL and external guys. So thanks a lot. They really made this demo possible. And all right, on this bright note, I would like to conclude my presentation and wish for a brighter future for the Scala tooling ecosystem. Thank you, guys.
Thank you, Eugene. I think we have time for one question, if there is any. We have some questions already, but Ilya.
All right.
Okay.
So Ilya has a question.
So are you sure that's even possible to map those trees? But I mean, if it was possible, all of these other tools would have probably managed to build something on top of those trees too. Isn't it the same problem, basically?
Okay. Is it possible? Well, of course, I'm obligated to say yes, otherwise I wouldn't have come here, right? But I just think that it's really tricky, and it needs a focused application of effort, something that, for instance, master students cannot afford, or, you know, hobby programmers who have day jobs they cannot afford. So I think we really need to get together and just handle this. And once we have a working implementation, it will become easier because we'll be able to synchronize it with, you know, the evolution of different compilers. After all, the desugaring schemes, they don't change that much. So once we have a working thing, it'll be okay to maintain. So that's my current opinion, at least. Maybe future will change it, but yeah, let's be hopeful. Okay, any other questions, or do we have to wrap up?
Okay, so let's go.
Could you name, please, some open source projects that use your library and provide some high-level logic to us?
Okay, so far, I do not know of libraries that provide wrappers for ScalaMeta. So the only projects that I know, they're essentially started by some of my students or people who we've been in contact with. And as such, they just use ScalaMeta to achieve their goals. Like, for instance, Olaf uses it to format Scala code. I hope that as the library matures, if it becomes useful to the community, then we'll get to see things that you're talking about, but not at this stage.
Okay, thank you, Eugene.
All right, thank you, guys.
After the lunch, we will have a few lightning talks, 3 of them actually, and a little bit of word about expression evaluators, async debugger a bit later. That are pretty useful tools for you on your daily basis. And also Pavel from IntelliJ team will present will present Scala plugin for IntelliJ. So still a lot of things to come, and right now we have a lunch break. So 1:30, we'll meet again for the next presentations. We will start with lightning talks. Thank you.